This is a detailed answer for example 1 from chapter 8. And examples 2 through 5 are modifications of example 1, and I will provide a detailed answer for each of those as well. And here's a graph of all 5 examples of distance as a function of time. I'll provide some background information for each example and how I learned to think about each of these examples as I went through the calculations. And here's the text for example 1. This is the equation right here. This is distance as a function of time. Actually, it's a function of time squared. And you're to find the velocity and acceleration at 5 seconds, 100 feet. You're going to calculate the average velocity at 10 seconds. Here are the 3 equations. Distance as a function of time, velocity as a function of time, and acceleration as a constant. Here's the calculation for time at 5 seconds, distance at 100 feet, time at 10 seconds, and this gets to calculating the average velocity compared to the instantaneous velocity at 5 seconds. So average velocity at 10 seconds, and how does that compare to the instantaneous velocity at 5 seconds? There are 10 calculations for example 1. So this is 1 through 7, and then 8, 9, and 10. And I show you where each of those calculations is in a table of distance as a function of time, velocity as a function of time, and acceleration as a function of time. So here are those 10 calculations. 1 through 10 is right here. And where does each of those calculations show up in the graph? So here's 1 right here, and here's 10 right here, and the remaining calculations show up in this graph. Okay, so let's get to the details. Chapter 8, Example 1. This edition was published in 1992, and it has some additional chapters by Martin Gardner, and he cleaned up the language a little bit because this book was originally published in 1910, so that's 113 years ago. It was very popular. It was reprinted several times, and the second edition was shortly thereafter in 1914. In Chapter 8, there are 6 examples. 5 of those examples are variations of this quadratic equation right here, which describes the distance a body moves as a function of time. Example 2 is a variation of that. 3, 4, 5 are all variations of the same initial quadratic equation. And so here are all the graphs of all 5 examples. Here I zoomed in on the same graphs, and you can see that at time 0, so this vertical axis right here is time 0. At time 0, all 5 examples are 10 4/10 feet to the right of point 0. Here's point 0 right here, and at time 0, all 5 bodies are 10 4/10 feet to the right of point 0. And example 1, which is the blue graph, and example 4, which is this purple graph, both are at rest at time 0. That's not true for example 2. Example 2 is at rest right here at negative time. Example 3 is at rest right here at positive time. And example 5 is at rest at 2 different places. This point right here is negative time, and this point right here is positive time. Here's the text for example 1. So this is the equation right here. So distance is a function of time squared. Time is in seconds. Distance is in feet. Have to find the velocity and acceleration at 5 seconds, 100 feet, 10 seconds. This is the average velocity at 10 seconds. And compare that average velocity at 10 seconds to the instantaneous velocity at 5 seconds. So all of this is getting to the average velocity. This right here this is the 100 feet, the calculation of the time it takes to travel 100 feet and the instantaneous velocity at 100 feet. Time at 10 seconds, figure out the average velocity, and compare that to the instantaneous velocity at 5 seconds. So I'm going to go through some background information right now on what we're supposed to do. So x feet is equal to this quadratic right here, time squared. Here are some equations that the author goes through in this chapter. So distance, velocity is the first derivative of distance. Acceleration is the second derivative of distance. Force is equal to mass times acceleration. So if acceleration is the second derivative right here, so force is equal to mass times that second derivative, and work is equal to the distance times force. So if this is force right here, mass times the second derivative of distance, then work is equal to distance times mass times acceleration, which is the second derivative of distance. We're supposed to find the velocity and acceleration at 5 seconds, At 100 feet, the average velocity at 10 seconds. This is the first derivative of the equation up here, which is velocity is equal to 4/10 times the time. This is a linear equation, and it's also proportional to time. And acceleration is equal to the second derivative, and this is constant, does not change over time. It's 4/10 feet per second squared. So you begin to look at these problems, and the initial calculations are pretty straightforward. Time, when time is 0 seconds, that body is 10 4/10 feet to the right of point 0. So the body is at rest when velocity is 0. So the object is at rest. And the distance is 10 4/10 feet to the right of point 0. And point 0 you can think of as the observer. So what I did is I put these 3 equations into a spreadsheet, created tables for each of the 3 equations, graphed each of the 3 equations, and then I could begin to put together the story for each of these. So distance, time, velocity, and acceleration. And so as I look at each of these 5 examples, you begin to realize, calculate the velocity at rest. You know the velocity is 0, so use that velocity equation to figure out the time at rest. That time at rest is 0 for example 1 and example 4, but not true for examples 2, 3, and 5. And what's the distance at time 0? It's always 10 4/10 feet, but when the body has traveled that distance, that body is not always at rest. So once again, it is at rest in examples 1 and 4, but not at rest in examples 2, 3, and 5. So here's the table that gets generated. Here's the graph that gets generated. This is distance versus time. Let's go through each of those equations. So here are the 3 equations right here. So when the object is at rest, velocity is 0. So when velocity is 0, time is 0. So time is equal to 0 divided by 4/10. Time is equal to 0 seconds. So that body is at rest when time starts. And at that same time, that body is 10 4/10 feet to the right of point 0. So it's starting at 10 4/10 feet to the right. So point 0 at rest. So replace time with 0. And you get distance is equal to 10 4/10 feet. So in the tables, time is 0, the distance is 10 4/10 feet. So this is calculation number 2. And the velocity is 0, so that body is at rest. This is calculation number 1. And the acceleration is 4/10 feet per second squared. It is always 4/10 feet per second squared because acceleration is constant. Turns out that this distance is the closest that this body comes to the ground, or 0 distance. Right here, closest that body travels to the ground to 0 distance is that it gets 10 4/10 feet to the right. So this is both calculations 1 and 2. So 5 seconds after rest is just in the distance equation, replace time with 5 seconds, and you get that that body has now traveled 15 4/10 feet from point 0. Now it's really only traveled 5 feet because it starts at 10 4/10 feet to the right of point 0. And so the distance that is to the right of point 0 in 5 seconds is 15 4/10 feet. The 5 feet plus the initial 10 4/10 feet. The velocity at 5 seconds after rest, replace time with 5 seconds. That velocity, that instantaneous velocity, is 2 feet per second. The slope of 4/10 feet per second is equal to 1 foot every 2.5 seconds. So 1 over 2.5 times 5 is 5 divided by 2.5 is equal to 2. So every 2.5 seconds, that body moves 1 foot per second faster. So in 2.5 seconds, it's at 1 foot per second. At 5 seconds, it's at 2 feet per second. At 7.5 seconds, it's at 3 feet per second. And at 10 seconds, it will have an instantaneous velocity of 4 feet per second. So at 5 seconds, the distance traveled is 15 4/10 feet. The instantaneous velocity is 2 feet per second. Here's the velocity at 2.5 seconds, 1 foot per second, 2 feet per second. At 10 seconds, it's 4 feet per second. At 20 seconds, it's 8 feet per second. So velocity is proportional to time. Double the time, 2.5 seconds to 5 seconds, double the velocity. Double the time again, 5 seconds to 10 seconds, double the velocity. Double again, 10 seconds to 20 seconds, double the velocity. So on the graph, you go out here to 5 seconds, go up to this point. This point is 15 4/10 feet to the right of point 0. And that instantaneous velocity, the tangent at this point, will have a slope of 2 feet per second. At 10 seconds after rest, that body is now 30 and 4/10 feet to the right of point 0. So it's 10 squared, 2/10 of 100 is 20. 20 plus 10 and 4/10 is 30 and 4/10 feet to the right of point 0. And the velocity at that 10 seconds is 4 feet per second. That's 4 times 2.5. 4/10 feet per second is the same as 1 foot every 2.5 seconds. So 10 divided by 2.5 is equal to 4. So here's calculation 5. The distance at 10 seconds is 30 and 4/10 feet to the right of point 0. And the velocity at 10 seconds, the instantaneous velocity at 10 seconds, is 4 feet per second. Again, the acceleration is constant, so it's 4/10 of a foot per second squared. 4/10 of a foot per second each second, which is the same as increasing 1 foot per second every 2.5 seconds. So go out to 10 seconds on the graph. The body is now 30 and 4/10 feet to the right of point 0. So this is 30 and 4/10 feet right here. So 20 feet plus 10 and 4/10 feet. So 30 and 4/10 feet. And the instantaneous velocity at this point is 4 feet per second. Traveled 5 seconds longer in time, so that means it's increased its velocity by 2 feet per second. So what's the average velocity at 10 seconds? Well, the total distance traveled in 10 seconds is 20 feet. So it's at 30 and 4/10 feet to the right of point 0. But remember, it started at 10 and 4/10 feet to the right of point 0. So you have to subtract that 10 and 4/10 feet. So that body has traveled 20 feet after rest. When time was 0, it was at 10 and 4/10 feet. So that 20 feet divided by a total time of 10 seconds is 2 feet per second. That is equal to the average velocity. And that average velocity is equal to the instantaneous velocity for half the time. So that makes sense, because the instantaneous velocity at 10 seconds is 4 feet per second. So 4 plus 0 is 4, and divide that by 2, you get 2 feet per second, and that's half the time interval. So the instantaneous velocity at 5 seconds is 2 feet per second. Here's the instantaneous velocity at 10 seconds, 4 feet per second, and that average velocity is half the time interval, which is an instantaneous velocity of 2 feet per second. So on a graph, the average velocity is the slope of this line that connects these 2 points. Here's the distance at time 0, the distance at 10 seconds. So that total distance traveled is the difference in these 2 distances at 10 seconds and at 0 seconds. And the total time it takes to travel that distance are these 10 seconds. That's the slope. That's also the average. So you begin to realize that the calculation of the slope between any 2 points is the average between those 2 points, because you're calculating the total distance moved divided by the total time it takes to move that distance. Now the instantaneous velocity at half that time interval is the same. The slope of this tangent at half the time interval is the same as the slope for the average velocity. And again, that makes sense. This has an instantaneous velocity of 4 feet per second. This is 0 feet per second. The average velocity is half of that 4 feet per second, or 2 feet per second, which is at half the time interval. So the average velocity is 20 feet divided by 10 seconds. It's equal to 2 feet per second. 10 seconds after rest, the instantaneous velocity is 4 feet per second. 5 seconds after rest, so half the time interval, the instantaneous velocity is 2 feet per second, which is equal to the average velocity over twice the time interval. So rather than 5 seconds, it's 10 seconds. So whatever 2 points you choose, that relationship has to hold. The average velocity will be equal to the instantaneous velocity at half the time interval. So choose a different time interval. So 5 seconds. The distance traveled in 5 seconds is 5 feet. So that's an average velocity of 1 foot per second. So 5 feet divided by 5 seconds is 1 foot per second. So if you go out half the time interval, so 2.5 seconds, the instantaneous velocity has to be that same 1 foot per second. So the velocity at 2.5 seconds, half the time interval, that instantaneous velocity has to be equal to the average velocity over 5 seconds. And it is. It's 1 foot per second at 2.5 seconds, and the average velocity is 1 foot per second after 5 seconds. The slope of this tangent, you move this over, slide this over, it's going to match the slope of the average velocity for 5 seconds traveled. So the object at point 0 This is solving for the roots, or the solution to this quadratic equation. So at what time is that distance equal to 0? And it turns out that there is no time when the distance is equal to 0. Because time is equal to the positive and negative square root of a negative 51, that is not a real number solution. It is a complex number. It has an imaginary component and a real component. So there's no real solution because that graph shows you that the body never is at point 0. The closest it gets is 10 4/10 feet to the right of point 0. It never reaches point 0. It never gets down here to point 0. So it starts at 10 4/10 feet to the right of point 0, 100 feet out. To replace x with 100 feet, solve for time. And there's both a positive and a negative value, which is 100 feet out, and that is at 21 and 1700 seconds. And a negative 21 and 1700 seconds is also 100 feet to the right of point 0. It's velocity, so now you know the time. So now use that in the velocity equation, and you can calculate the velocity at 100 feet as 8 and 468 thousandths feet per second, both a positive and a negative value. So 100 feet before rest, or before it reaches this 10 4/10 feet, and 100 feet after rest, or after it travels past this 10 4/10 feet. So 100 feet before rest and 100 feet after rest. Both of those cases is 21 and 1700 seconds away from time 0, either before time 0 or after time 0. So 100 feet before rest and 100 feet after rest. Now this is 100 feet from point 0, not 100 feet from rest. And you see here that it's actually 89 and 6/10 feet from where the body is at rest. So this is 89 and 6/10 feet. This 100 feet right here is 89 and 6/10 feet from where the body is at rest. And this is 89 and 6/10 feet from where that same body is at rest. And the object at time 0, when the timer starts, so time 0, once again that body is 10 4/10 feet to the right of point 0. And then if you calculate the time when x is equal to 10 4/10 feet, plug that back in, you're going to get time is equal to 0. It has to make sense. So when time is 0, the body is 10 4/10 feet to the right of point 0. And when the body is 10 4/10 feet to the right of point 0, it is at time 0. So you're just going back and forth here. So at time 0, the closest that body gets to point 0 is 10 4/10 feet to the right of point 0. And that body is also at rest at time 0. So here's the body at rest once again, 10 4/10 feet to the right of point 0. So calculation number 1 is the object at rest. So the velocity is 0, calculate the time. Calculation number 8, when the distance is 0, calculate the time when the distance is 0. In this case, there's no real solution because the body is never at 0 feet. And where's the object at time 0? Calculate the distance with time is equal to 0. And here's a line diagram that shows distance from point 0. So here's point 0. You're going this way. This is distance, is the black, and the time is the blue. So it's starting at 10 4/10 feet from point 0. This is time 0 right here. So 5 seconds, 15 4/10 feet. 10 seconds, 30 4/10 feet. 21 and 1700 seconds is at 100 feet. Remember, there's no solution. There's no time to move from point 0 to 10 4/10 feet to the right. The timer starts at 10 4/10 feet to the right of point 0. And that's the closest that the body gets to point 0. So I drew this circle, has a radius of 10 4/10 feet, because you're not sure where that body is. It's defined as being 10 4/10 feet to the right of point 0, but it seems to me it could be anywhere. And you could even imagine this in 3 dimensions as a sphere with a radius of 10 4/10 feet, and it travels that 10 4/10 feet to this point right here, and then it starts moving to the right of point 0. I don't know if that's true or not. It just seems like that's a way to think about it. In thinking about the graph, I realized that the body travels left from the right. It comes to rest, turns around, and then it moves off to the right. So this is a better diagram of what happens with the movement of that body. For a more detailed discussion of the movement of the bodies in examples 1 through 5, watch this video. This is the simplified version that includes a discussion of all 5 examples.